Good afternoon. My name is Dele Ogunshaitan, and I'm delighted to welcome you to our public health seminar series. It's midway through the quarter. I see some of our distinguished faculty members walking in now, so we're delighted to have everybody. This seminar series, first I should thank the Office of Extension for helping us videotape this seminar series. So we know not everybody can come every day, for those for whom it's not required anyway. This seminar series is archived through the UC Irvine Open Courseware website. So if you missed any of the previous seminars, it takes a few weeks before the videos are put online. But we go back now about 4 years, so it's quite a resource for everybody on campus as well as off campus to access seminar series from the past. And this series is made possible in part because of the network that our faculty members have established through their own research, service activities, colleagues from all over the world. And today's speaker was nominated by Dr. Scott Bartel. Scott joined us several years ago now. He's associate professor in the program in public health, but his time is also in high demand. He's a faculty member in the Department of Statistics as well as in the Department of Epidemiology. He teaches epidemiology courses and statistics courses at the undergraduate and graduate levels. And for those of you who don't know his work, I encourage you to look up his website, not to bombard him with emails, but he certainly would be delighted to talk with you more. So join me to welcome Dr. Bartel, who will introduce the speaker.
Okay, usually I'm loud enough that you can be heard without the microphone, but I'm working a little bit of cold, so I'm going to rely on this right now. I'm very happy to have Dr. Jeremy Sarnat here today to talk about his work. He's been in air pollution research for a long time and he's actually at Emory University now in faculty, completed his doctorate at Harvard in 2002. I first met him shortly after when he joined the faculty at Emory while I was still working there before I came to UC Irvine. Now, Jeremy's very interested in the interface between exposure assessment and epidemiology, and particularly it applies to air pollution. And he's written several highly cited papers on the implications of exposure surrogates like ambient PM or ambient gaseous pollutants, surrogates for personal PM exposure, and on the impacts of exposure measurement error in air pollution epidemiology. In 2011, he won the Outstanding Young Scientist Award from the International Society for Exposure Science, yet he remains a very modest and friendly person. So I really encourage students to come introduce yourselves after his talk. He's very approachable, and he also has some very interesting experiences and connections. He's actually had some jobs outside of academia, so he's a really good person to talk to about career advice for those of you who are thinking of pursuing environmental health as a career. So without further ado, Dr. Sarnat.
Thank you, everybody, and thank you very much, Scott. Is this too loud? Maybe. For inviting me in the introduction. I was very excited, actually, to be invited out to lovely, sunny, warm Southern California from Atlanta. And another thing that actually, I'll just start with a quick anecdote, but a few years back, actually, Scott came back to Atlanta to meet with us, and he actually stayed with us a couple nights at my house in Atlanta, and now I'm staying with Scott. He's hosting me now. And the thing that he didn't mention, or he won't mention, is that actually I made him go to work. I had him clip my hedges at my house to stay at that place, and he did not do the same for me since I've been here, so I appreciate that, Scott.
Yeah, anytime.
So I'm going to share with you today a bit on some research that I've been conducting, a study that's currently ongoing, and I think it is a topic that is of great interest to many in this room here, and I'm going to put some of this stuff out there not only just to share it with you, but also hopefully that this will encourage a dialogue and to get your feedback and perhaps even promote some future collaborations. It looks at commuting, car commuting in particular, and acute health response. And I'm going to talk a bit about some results from a series of studies that we've called the ACE studies, one of the most overused acronyms in academia, I know, the Atlanta Commuters Exposure Study. I entitled this, "Is Commuting Really That Bad for Your Health?" Many of us probably have opinions about this particular question right now. And it's a topic that is very much in the news today. We know that commute times have been rising for actually decades now. And that not only is the time that we spend in our vehicles increasing, but the time in congested traffic also increasing. And there were patterns or decreasing trends in congestion that were due to the economic downturn, but now we're seeing that as things are picking up, the congestion times and patterns are increasing as well. There was a study that actually came out last month from a social geographer from Sweden that was cited in many of the media sources with very foreboding titles, headlines here, "Commuting to an Early Grave," that looked at a number of potential risk factors associated with commuting. And in fact, here's another article that cites the same study from the Swedish geographer. More research reminds everyone that long commutes literally kill you. And in the sort of blurb here underneath, it says, "Research revealed that people with long commutes are also 40% more likely to separate or divorce." So we're not just talking about acute health response, but other social factors as well that seem to be associated with commuting. But the question is, really, what is driving increased morbidity, mortality, divorce, separation? What are the factors that we're most concerned about with commuting? There are possibly a number of plausible factors that could explain these associations, these observations. It is stressful at times commuting long distances in heavily congested traffic. There is increased trauma from being in accidents associated with driving. Physical inactivity we know to be a major risk factor for a number of endpoints. And of course, our exposure to a number of pollutants while commuting is a topic that is one that is of particular interest to me. It is the source of a lot of the research that I conduct. But there's still many questions associated with pollutant exposures, just generally, as well as while we're in a vehicle. Now, we should be concerned about exposure to air pollution because of the very troubling findings that seem to indicate that there is not really an adverse outcome that we know of that is not in some way related to exposure to air pollution. So when epidemiologists and toxicologists first started doing studies of the link between air pollution and adverse health response, naturally they looked in a number of systems in the body. The first set of responses that we were most interested in were naturally where? What system of the body? In the lungs, in the respiratory system. And sure enough, we have over many decades now established a formidable body of scientific evidence that does link exposure to air pollution with many adverse respiratory responses. Some of the responses are things that we may actually consider to be relatively mild, or irritations, to exacerbation of existing respiratory diseases, to quite severe endpoints as well. As we begun to sort of look deeper into other systems and to understand a bit more about the potential mechanisms that could explain why we're seeing these effects in the lungs, we began to observe effects in other systems too. There is emerging evidence of associations between exposure to air pollution and adverse reproductive responses, low birth rate due to births, perhaps increases in certain birth defects of mothers who are living in areas with high air pollution levels, even within this program and within the school, there is interesting research that is sort of shedding light on these potential associations. I'd say that right now it's not necessarily conclusive, but certainly suggestive. Adverse neurological endpoints as well that have been associated with exposure to air pollution. And a lot of research has looked at the link between what we breathe and its impact on the heart. Adverse cardiovascular effects. Again, there might be changes in what we may consider to be subclinical changes in biological changes, increases in certain markers of inflammation, both in the heart but systemically too, changes in our autonomic function, cardiac autonomic function, increased heart rate, changes in the variability between the heart rates, the beats, increase in atherosclerosis, and CV death as well, cardiovascular death as well associated there. So we are very concerned about air pollution and its effect on health, not just its effect on our lungs. And there's a number of ways that we have actually tried to build the weight of evidence that have led to these observations, to these links as well. We may be familiar in this, well, everyone should be familiar within this program that we have different ways, different approaches for conducting studies, controlled studies. Sometimes we talk about them as toxicological studies, where we have a lot of control over the experimental design. We can look at specific exposures and endpoints in a very highly designed, controlled manner. We have another body of designs, of studies, of approaches for looking at these associations that we sort of collectively refer to as observational studies or epidemiology. And these are studies where we actually look and see what happens when specific parameters in the environment, in this case in air quality, change and corresponding changes in health within a specific study population. Sometimes we'll sort of refer to, or we'll classify the observational studies by whether or not they're done within a population which could be upwards of millions of people, looking at observations between air pollution and corresponding response within a major or a large population. And depending upon what kinds of health effects we're interested in, whether or not we're looking at things that are occurring acutely over a long period of time, chronic endpoints, we may design those specific population studies differently in either a longitudinal way where we look at day-to-day changes in air pollution, say for instance PM 2.5 and a corresponding health endpoint within a population. In this case, these are just a schematic that demonstrates asthma emergency department visits. So we can look and see in some of these population-based designs what happens when with trends in a population or trends in a given city, say, in a specific parameter and corresponding response, say, in emergency department visits. There's another sort of set of epi or observational designs that have been employed, perhaps not as commonly as some of the population-based approaches, but they're sort of done in smaller settings, panel-based or cohort studies, we like to call them, rather than looking at changes in exposure or pollution in a large population of millions. We may actually look at exposures that are occurring in some cases tens or dozens of subjects and a body of other health endpoints or health measurements as well. And here too, just like with the observation studies, we're looking at, with the panel or cohort studies, daily, multi-day, and in some cases we may be looking over many years with some of the larger cohort studies of their exposures. And in this case, we can look and we can measure many different endpoints. In some cases, they might be clinical. In other study designs, panel-based study designs, we may be actually looking at subclinical changes too. And these have actually emerged as a very powerful tool and technique for elucidating these links that in some ways we haven't been able to actually clarify by the use of larger population-based designs. Let me elaborate on that. They also happen to be the approach that I've used in most of my studies, panel-based studies on air pollution and health, and I know that folks and researchers in this room as well have also been prone to use these panel-based approaches in looking at observational associations with air pollution. So panel-based studies are quite unique, and they provide a number of different advantages over population studies, in that with these studies, and given the fact that usually we're dealing with smaller groups, panels of subjects, we can conduct, in many cases, very good exposure assessment as well as a measurement of health as well. And so that where we may actually have a bit more limited power to look at associations in smaller sample sizes, we offset that lower end, that lower sample size, by a much stronger, more accurate exposure response characterization, which we hope will reduce some of the error that might be associated with trying to assign exposures over broad populations. And what we've seen is that we've actually been able, within panel studies, to see things that, as I said, that we have not been able to see in some of the population studies. The ability to look at a range of different endpoints, not just clinical response, but in some cases specific biomarkers that may be indicators of different steps along a subclinical pathway, have also allowed us, through the use of the panel studies, to address a lot of mechanistic questions about exposure to air pollution. Like other EPI studies, we look at real-world settings, and in many cases, these are very complex mixtures of pollutants that, in a controlled exposure setting, in a toxicology study, we may not ordinarily be able to look at through the design itself. And with the panel study as well is that while it's not at all a controlled study, like a toxicological assay, in many cases we can employ quasi-controlled designs, and I'm going to talk with the ACE studies, the Atlantic Commuter Exposure Studies, about how we try to implement a quasi-controlled design with this particular panel study. I just wanted to put up a couple of pictures from studies that I've been involved with that might give you a sense of some of the types of measurements we'll be looking at within these panel studies. This actually is a device. This is a friend of mine who actually is a faculty member in Taiwan right now, who for his doctoral thesis wanted to look at exposure, and in this case, the air pollution exposure that was in somebody's breathing zone to a number of different particle and gas pollutants. And he sort of dragged this device with him throughout Baltimore. And what we were able to do with this study, what he was able to do, was to get a very accurate and highly temporally resolved distribution or measurement of exposure to a range of different pollutants, again, that was in this subject's, in this case my friend's, breathing zone. So you can see that this is in many ways much different than perhaps an approach that we might use in a population-based EPI study, where as a measure of exposure assignment, we may use a central site as a surrogate of exposure for an entire population. Now, I will say that this is in many ways a very cumbersome approach towards characterizing exposure. I think it's sort of a sad state of geopolitics, of the social climate today, where I don't know if you'd really actually be able to do a study like this today. Right? It would be a very short study. You'd walk out in a few minutes and then he'd get tackled and that would be the end of the study. So, but we do use other less cumbersome and less elaborate measures within these panel studies to get them a very good, accurate measure of air pollution, of exposure to a range of different pollutants. And in this case, too, we can look at a number of different endpoints, not just clinical endpoints, but other subclinical endpoints as well. So we do have questions about generalizability. If we're looking in tens of people and dozens of people rather than millions of people, how applicable or generalizable are the findings from these studies to broader populations. Things to consider with panel-based designs, and they can be very expensive as well. A panel study that generated a lot of interest and in some ways provided a lot of the scientific impetus and motivation for conducting a commuter-based study was one that was published in the New England Journal of Medicine in 2007 that many of us may be familiar with, that looked at a group of asthmatic subjects. This was a panel-based study that was conducted in London, England. And what the researchers did was they had this group of asthmatic subjects, older adults, walk on 2 separate days in 2 separate areas of London. One was on Oxford Street in London, which is a very heavily trafficked area of the city that has lots of diesel buses and other traffic-related exposures. And then on another day, they had these subjects walking in Hyde Park, which is probably about as far as you can get from this environment as you could within London. And what they did was they first characterized, and they had very good exposure characterization. They had carts that were following around these group of older adults when they walked in this area and in this area. And they looked first at what the differences in the exposures were to a number of different traffic-related pollutants. And you can see that I just put up as a little sample the different exposures that were measured when the subjects were walking in Oxford Street compared to Hyde Park. This is for elemental carbon and nitrogen dioxide, which are 2 major components of traffic emissions, vehicular emissions. When they were in Oxford Street, you can see the difference in concentration for elemental carbon and nitrogen dioxide. And these were highly significant differences. So from an exposure design standpoint, this was a good design, a good study to look at what happens. And then this is also an example of a quasi-controlled panel design when you bring people in this environment and that. And then they looked at a number of different endpoints, and this just sort of shows what the acidity of the exhaled breath was in these subjects when they were walking here compared to here. So these empty bars over here looks at the acidity when they were in Hyde Park, and then the colored shaded bars over here look at the acidity of their breath when they were walking in Oxford Street. It's more acid, an indicator of pulmonary inflammation perhaps when they were near the traffic emissions. So this led us to think, many of us actually, very interesting findings, and that we were able to sort of see these differences, a very creative design, but we were able to see these differences in a relatively small panel of subjects, to look at other environments, microenvironments, where we may be exposed to very elevated levels of traffic pollution. And it led us to propose the first of 2 of what are now 2 Atlanta commuter exposure studies. These studies are quasi-controlled in that we actually recruit participants to be a part of the study and to conduct a 2-hour commute in Atlanta morning rush hour traffic. And what we have with both of these studies, and I'll tell you the differences in a second between the first ACE and the second ACE study, but we have very good measurements inside of the vehicles of the subjects. And these were everyone's subjects' personal vehicles. So we have good measurements inside of their vehicles during the entire 2 hours. And we also conduct a range of different health measurements before they begin their commutes and at various time intervals after their commutes to see if there are changes that are occurring as a result from the exposures. And the goal for these exposure studies broadly are to look at the associations between what they're exposed to, different mixtures that could be eliciting response in this population that generally follow an oxidative stress mediated biological pathway. And I'll get into that a little bit more, but not too much here from the mechanistic side. The first of the studies was actually funded by CDC, and it included 40 subjects, 20 non-asthmatics and 20 asthmatics. And each of the subjects participated, and they did 2 highway commutes. And they came into our clinic, and they went out on the road for 2 hours twice. And the second study, which is actually part of an EPA-funded center that we have at Emory, looks at 30 non-asthmatics and 30 asthmatics. And the main difference here that I'll talk about a little bit more is that we actually have a controlled exposure as part of this particular study that the first ACE study did not include. So we know that exposure to traffic pollution during a commute is very elevated, and a number of groups, investigators, a lot of folks at USC and UCLA have looked at what fraction of one's exposure during the course of the day could occur while they're actually doing their commutes. And it could be very, very substantial for many people, especially for people with long commutes. And in Atlanta, that happens to be a lot of people. About 3/4 of the working population has an average one-way commute of 30 minutes, so that 3/4 of the working population in Atlanta is in their car for at least an hour a day. So Atlanta is a very good place, I think, to do a study looking at commuting in vehicle pollution and health. But Southern California is actually also a very good place too. A lot of times when I present these results, it's I can one-up everybody on how bad the traffic is, but I don't know if I can one-up everybody. And that's why you guys have looked at traffic too in this area. So what were the questions of interest when we designed the ACE studies? Well, first, can exposures while commuting lead to adverse health, to acute response, health response? Is it perhaps worse for some people more than others? And in this case, are we seeing any differences in response among the asthmatics? Is there heterogeneity in response among the asthmatics themselves? Are some components more responsible for any observed responses that we see in the subjects more than others? Are some things worse about traffic more than others? And specifically here too, we wanted to look at the question of non-chemical pollutants or stressors or emissions risk factors. We know that when we're driving, it can be oftentimes either noisy or stressful experiences. Those are two factors that could also perhaps be associated with adverse response, similar to what might be elicited from a pollutant exposure. Taking a bigger picture and trying to contextualize the work, I guess the question is, should we view commuters, daily car commuters, as being perhaps vulnerable to air pollution, health effects, or other enhanced risk more than other populations? And finally, something that all too often I don't know if I really think or spend as much time thinking about is, but what is this sort of general translational or public health message associated with findings like these panel studies? What can we say about results that are done in small groups of individuals? Where does it fit within the body of other work that's being conducted as well? So I thought that with the remaining time, we'd go and try to address as many of these points as we can, just to sort of tell you or show you from a schematic perspective what would happen during these studies, what happens. One of the studies is ongoing. I should mention ACE2 is about 3/4 done, and the first ACE study, the one that I'm presenting results on, was completed about 1.5 years ago. So as I mentioned, subjects generally would come into Emory. We would visit them about a week before the commute, conduct baseline health surveys. The day before they actually did their commute in the afternoon, we would actually fit the subjects with a number of different instruments and sensors that looked at specifically heart rate or cardiac autonomic function. The next morning they would come to Emory. We did have criteria that all of the subjects that participated in the studies would not actually be driving long distances to get to their long distance drive, which could be a potential introduced error and bias into the analyses. At around 7 o'clock, they would actually leave the Emory facilities and begin their 2-hour commute, and they would get back around 9 o'clock. At 9 o'clock, 10 o'clock, 11, and then 12 noon, we would conduct follow-up health measurements similar to the ones that we conducted before the commute. So we had an ability to look at potential response immediately after a commute, and then various time lags after a commute. We know that the processes and the mechanisms by which pollutant exposure may provoke or elicit a response, in some cases may have actually substantial lag periods. And for a lot of endpoints of interest, a 12 noon as final measurement period will probably not even catch or begin to catch any response, an initial response for these markers. But this is what we have. We had a number of different measurements that I'll talk a little bit more about, both health measurements as well as pollutant measurements. We had to design from an exposure standpoint, from a measurement standpoint, this was is a very challenging project. A lot of the pollutants that we might be interested in that may be associated with traffic emissions are present in only trace concentrations. So that in order to measure them, we actually had to collect a lot of mass. Most of the pollutants that we were measuring for this study, or I should say exclusively for ACE1, were particulate pollutants. So in order to sample these trace elements, we actually had to employ, as you'll see in the next slide, a very intensive set of pumps and samplers, and the manifold itself that we put in every person's vehicle was quite intensive to get enough mass to have enough analytical power to actually reliably report these concentrations. We had a number of different continuous measurements. These are things that a lot of us who have done air quality research have used, looking at particulate or fine particulate matter mass and ultrafine concentration, black carbon, which is an indicator perhaps of diesel, and PAHs. We had a number of integrated measurements, and these were to get at some of the species, both the elemental as well as organic species of particulate matter in the vehicles during the commutes. And these, I think, offer kind of a more novel look into what might be the composition and the nature of exposure occurring. In terms of the species that we might be most concerned about, since we were thinking that perhaps a lot of the response might be due to provoking of an oxidative stress pathway, we were interested in a lot of the transition metals as well as the PAHs. This is what some of the equipment looked like inside of the vehicles. They were in the front seat here. You can see some of the continuous instruments and some of the impactors. And in order to actually sample enough mass, we had to have lots of pumps and huge batteries in the backs of the cars too. And I will say that when driving in a vehicle that is outfitted like this, apropos to my previous comment about doing studies, nobody was ever pulled over, which is probably a good thing. But we did have a little sticker on the side of the car that said that you were participating in an instrumented vehicle. But it was quite an elaborate setup, just from an exposure standpoint, to characterize these different pollutants. I did actually want to take you on one of the commutes, but I don't think I'll be able to do it. Maybe if I have a bit of time at the end of this talk, I downloaded a flash file that had actually the camera from the front of a vehicle that looked at what a commute looks like, and then the corresponding pollutant concentrations as you encounter different emission sources while on a highway. It's sort of a cool thing to look at, and you get a sense of what we were actually interested in, and the power of actually sort of sampling in this way to look at whether or not perhaps peaks in exposure, maximum concentrations of a given pollutant might be generating a response, or whether or not you can sort of see generally elevated levels of different pollutants that may also explain corresponding health response. These are the results, the summary results of the first ACE study. And if you think back to that New England Journal article, and you want to sort of see elevated levels in a quasi-controlled setting, and I just put some of the summary statistics for just a few of the pollutants that were measured and tried to put them in contrast or compare them to other studies that were conducted and are sort of similar in their design as well. So the ACE study, this is fine particulate matter, and black carbon or elemental carbon, PAHs, particle number concentration, which is an indicator of ultrafine particles. And for ACE, we see pretty elevated levels of a lot of the different pollutants while on the highway, which wasn't so much a surprise, but it was good that we actually had the ability to look at response from exposure to this in this particular setting. You can see for PAHs in particular, for these studies, for our study, concentrations were especially elevated during many of the commutes, which led to mean elevated exposures throughout the study. I'm not putting up a lot of the other speciated pollutants here as well. From a biological endpoint standpoint, from the health measurement side, we also looked at a number of different markers, biomarkers, and these relate to effects that may be occurring in different systems of the body, and keeping again with the idea that really exposure to air pollution has been shown in many ways to elicit response in different systems throughout the body. And I'm going to put this up. I don't really want to spend too much time on it. This sort of looked at our hypothesized mechanism. And I only put it up here, well, every one of these hypothesized mechanisms has many arrows. This is a very simplistic, in some ways, version of probably what is an extremely complex process. But I do put this up to sort of show that we hypothesized what might be occurring once somebody breathes in the emissions while commuting. And then we wanted, at the various steps in this really complex pathway, to see if we could find biomarkers that in some ways would indicate triggering of a different step along this process here. So we were looking at changes in redox chemistry and the ability of the body to respond to oxidants in oxidation. We looked at lipid peroxidation, changes in lung function, and cardiac autonomic function. And it does sort of fit together, but I'd be lying to you if I said I fully understood, as probably none of us do, exactly what might be happening mechanistically. I'm going to present some results now from the study, and the results are modeled in a couple of ways. I'm not going to go into the details of the modeling, but I will say that there were two primary ways that we looked at this. The first model was what we call a commute as an exposure model. We wanted to see changes in the biomarkers at various steps in the time intervals. And for these models, we actually don't even have pollution in the model. And it reflects this idea that it's an extremely complex exposure that might be occurring while commuting. It may include a range of different chemical species, but non-chemical stressors as well, stress, noise, other factors that can elicit response. Just trying to see at various steps in the protocol, the study protocol, whether or not the biomarkers changed at all during a normal commute, 2-hour commute. And then I'll present some initial results that show changes in biomarker at two different steps. The difference between a baseline concentration of a biomarker and then what the levels were after the commute as a function of changes, corresponding changes in pollution. So these are the pollutant models and these are the commute as exposure models. We modeled these using mixed modeling approaches, regression approaches. Be happy to talk about the specifications with anyone afterwards. I wanted to first put up some of the results showing changes at various time intervals with exhaled nitric oxide. Exhaled nitric oxide is a marker of pulmonary inflammation, which has been used pretty extensively in asthmatics as a sensitive indicator of lung inflammation. And we looked at the pre-commute levels, and then here are the estimates of, or the percent change post-commute at the various time intervals. So these are for all the subjects, both asthmatic as well as healthy subjects together. And we're seeing that immediately after the commutes, we have elevated significant increases in exhaled nitric oxide relative to baseline. They peak about 1 to 2 hours, and there's some indication of declining levels of exhaled nitric oxide at noon when they left, and we're done with the study for the day. These are the non-asthmatic subjects, and surprisingly, we see that this trend of increased elevated exhaled nitric oxide was significant, pronounced for the non-asthmatics as it was for the asthmatics. Similar trend with some indication, although I wouldn't read too much into it, that about noon or so we're beginning to see a return somewhat to levels before baseline, before they did their commute. There's also some, although it's marginally significant, differences between the asthmatics and non-asthmatics for this particular endpoint. Was very interesting. We also wanted to see if perhaps there may have been a difference among the asthmatics in how they responded. Generally speaking, this was a cohort of physician-diagnosed asthmatics, mild to moderate asthmatics. but they definitely varied. There was a bit of variability in how well they controlled their disease. And the way that we actually got at the level of asthma control was by using this tool, the Asthma Control Questionnaire, which consists of a series of 7 questions that looks at factors like medication usage, just symptoms over a period of time, as well as lung function. So we categorized the subjects by how well controlled or moderately or poorly controlled their asthma was, and we wanted to look and see if there were differences among asthma control in their pulmonary inflammation response expressed as exhaled nitric oxide. And this really gets at a mixture of things too, lifestyle factors, and asthma phenotype. So I'm putting up this graph now looking at, in this case, this is just the absolute change from baseline in exhaled nitric oxide among the well-controlled asthmatics. And you see that there is this elevation, the typical trend post-commute that we saw even with the healthy subjects among the well-controlled asthmatics. But for the poorly controlled asthmatics, you see a much more elevated and pronounced effect with exhaled nitric oxide, something that in this size study was a little bit surprising to us. So there is heterogeneity that we thought can be explained actually by administering this control questionnaire and by looking at how well their disease is controlled. If we look then to another marker that we collected within the lung, and this was the change in this biomarker of lipid peroxidation aldehyde in exhaled breath. So this also looks at oxidative stress and other perhaps downstream responses from oxidative stress in lipid within the lungs, lung cells. And we see an indication, although it's not significant among all the subjects, of elevated MDA in the breath. Among the non-asthmatics, you sort of see this, again, it's non-significant, and the asthmatics as well, the elevation is really occurring at the time period immediately post-commute. Now moving away from the lung and looking at markers of systemic inflammation, which we may hypothesize as perhaps occurring at later lags, longer lags from initial exposure. And in fact, much of the literature looking at traffic pollution and air pollution exposure and systemic inflammation, in this case we're using C-reactive protein, an acute phase protein associated with inflammation, as an indicator of systemic inflammation. Post-commute for all of the subjects, we actually did see a slightly elevated level of CRP, which after the first time period returns to baseline levels. In the non-asthmatics, as well as the asthmatics, the levels of MDA were highest immediately after the commute. Now these, given the sample size, I have to say, probably were not significant, but still I think suggestive that what we're seeing here could perhaps be associated with something experienced during those 2 hours. We move to cardiac autonomic function. And I'm sorry, I'm just sort of throwing this stuff out right now, but we'll try to tie it together in a second as we summarize. Looking at heart rate variability, in air pollution literature, there's the data are sort of all over the place in terms of what happens. Now, heart rate variability is actually, or a lot of heart rate variability is actually a good thing for our hearts. It sort of reflects our ability to adapt to changing environmental conditions. And that when you have reduced heart rate variability, some people feel that actually may indicate an adverse response. This looks at one particular marker of heart rate variability, SDNN, which looks at the different standard deviation from normal to normal beats. And these are each of the subjects in ACE, their SDNN levels before the commute, and then their SDNN levels immediately after the commute. The blue lines are subjects for which there was a decrease in heart rate variability among the 81 subjects. The red lines are subjects that actually were measured to have actually higher SDNN levels, greater heart rate variability after the commute. This needs fancy statistical or epidemiologic models to see that most people actually experience for this particular protocol reductions in SDNN. If we plot the data for SDNN as a percent of change from baseline, these were highly significant decreases in this marker of heart rate variability that began to recover to baseline levels afterwards for the non-asthmatic subjects as well as the asthmatic subjects, although for the asthmatic subjects we see much more pronounced effect on heart rate variability. I'm wrapping up here, so I did want to actually put up some changes in as a function, or the change, if we could perhaps explain some of the changes that we just put up as a function of air pollution measured in the vehicles. And here I apologize for the qualitative presentation of the results, but I think that there are a couple of points that I want to put up here. Here are the different health outcomes over here. Now, ENO, MDA, the lipid peroxidation measure, C-reactive protein, systemic inflammation, and SDNN, the heart rate variability. And we looked at a range of different pollutants and ways of categorizing the pollutants as well. Again, this is just a sample. We look at particle mass, ultrafine concentrations, black carbon, PAHs, and then we also wanted to see if, rather than the actual concentration of the pollutants, the number of events when elevated concentrations occurred could perhaps be more meaningful in explaining response with the endpoints here. The 3 points that I want you to take from this picture, and I just sort of shaded the boxes where we saw significant statistical associations with one of the different endpoints here. For ENO, the biggest predictor of elevations in ENO was actually water-soluble organic carbon. That's not a finding that it has been reported before. We don't exactly know what the source, however, of this water-soluble organic carbon is. Traditionally, people like to think of it as a secondary pollutant that's perhaps not associated with traffic emissions. However, in this case, we're thinking that it actually may be associated with traffic and a primary component of organic aerosol. So by far, the biggest, the most significant predictor of ENO was WSOC, water-soluble organic carbon. For MDA, on the other hand, we saw PAH, and in some cases black carbon, as being significant predictors of elevations, and in some cases they were significant associations with MDA, whereas the overall time trends from the first set of models were not significant. When MDA was actually modeled in these epi associations, we did see it to be a significant predictor. And there's a lot of endpoints where we did not see any significant associations with anything that we measured. And I wanted to bring this up only to say that we're sort of skimming the surface right now. I'd be happy to speak to anybody about ways to move forward, but in honesty, we probably think that what might be happening and the responses that we see from the first set of models could be due to exposure to a range of pollutants, to different mixtures of pollutants, figuring out the proper ways of categorizing the relevant, the ecologically relevant mixtures is certainly a task that we're all interested in, and we certainly have a lot more stuff to do. So we addressed a number of these questions today, looking at the response from commutes. Is it worse for some people than others? Perhaps beginning to look at what components of traffic pollution could be driving response. The questions about whether commuters should be viewed as vulnerable, especially vulnerable, and the public health message are, I'll leave that for a second. But what I think that we can say from the findings from the first A study that are still ongoing, but we're coming to the end of the analyses, that we did actually see associations or increased cardiopulmonary response after 2-hour exposure. Now, these exposures are actually experienced by many people on a daily basis. 2 hours is not an excessive amount of time to be commuting. Something that was somewhat surprising to us was that for many of the endpoints and some of the ones that we put up here now, that the trends, the general trends, while maybe not significant, were similar for both the asthmatic as well as the non-asthmatic subjects. There were some endpoints where we clearly saw a more pronounced, elevated response among the asthmatics, something that we hypothesized a priori. We did see some indication that perhaps some pollutants, that there was a differential response among these different endpoints by a different pollutant component. The WSOC fraction that we measured in our PM seemed to drive the ENO response more than other components, whereas the PAH seemed to drive the lipid peroxidation. And I think we're a bit early to sort of make conclusions about this right now. It's not too different than what others have reported as well. We don't know what the clinical implications are of these results. As I said, these are nearly routine levels for a lot of people throughout the country, throughout the world. And the question that comes up is, well, what happens when over the course of a lifetime or dozens of years, you experience these perhaps transient increases in inflammation and oxidative stress in response, what the chronic implications, health implications might be. We still have a lot more to do with these analyses as well, looking at confounding. And confounding, many of us know, is that when we sort of attribute or we misattribute response to something, we have an exposure of interest and outcome of interest, and then we have another factor that is correlated with both the exposure as well as the response of interest. In this case, there could be a number of potential confounders that we are not modeling yet. And that's why we've actually proposed to do the ACE2 study to try to flesh out what the potential role of stress, noise, other pollutants perhaps that we didn't measure could be on some of the results. With the ACE2 study, I should mention that, I did mention that we have a controlled scenario, so that for every subject that comes in to do this commute, they do a highway commute like ACE1, but they also do either a clinic visit, so rather than actually going out to do a 2-hour commute, they'll just stay with us at our clinic for those 2 hours, and we'll do the same set of health measurements. And some of the subjects will also do, as a more of a controlled scenario, a surface street rather than a highway commute to look and see if the responses are the same when we're exposed to a different mixture of pollutants, perhaps not as much from trucks. Now, I'm going to end with a comment that I got from a grant reviewer. This is when we first submitted the first ACE study years ago. And it was not funded initially to the place where we submitted the study. And this comment sort of ticked me off at the time. It said, okay, despite these very worthy objectives, I'm still a little confused about what the big picture issues are. Assuming the study does indeed find significant effects, which we did, what will be the implications for society? That people should avoid commuting? Hardly practical as a blanket piece of advice. So at first I read this and thinking as, oh, this is so well designed scientifically. I was so proud of myself to put together this and so you think of this idea. I was thinking of this. But the more I thought about this, the more I actually did begin to think that this relates to the last one here, which we haven't really even begun to address at all, which is the public health message. What do we make from findings from an ACE study or from the other panel studies or population studies? Where does it fit into policy about commuting, about air pollution, about tailpipe emissions? And down the line, in addition to the science that we've been presenting now, the questions about the translation and the effects certainly will become more and more important as well. So I just want to sort of end on that note there. This was, and these studies have been done by a very large group of investigators and currently continue to be conducted by many people's effort, including the subjects who participate in the study. So again, I appreciate any feedback, ideas, interpretation about what we can see, and as well the opportunity for working with you guys who have done such great work here as well, looking at air pollution and help. So thank you very much for your time and inviting me.